What if everything around you, the chair you're sitting on, the screen in front of you, even the thoughts in your head, wasn't quite as real as it seems? Imagine for a moment that the solid, predictable world you've always known is just a carefully constructed illusion, a fleeting shadow of something far stranger beneath the surface. This isn't science fiction or fantasy. It's a question scientists, philosophers, and thinkers have wrestled with for centuries, and the answers they've uncovered will make you see existence in a whole new light. Reality, as we experience it, feels fixed and unquestionable. But what if that's just the tip of the iceberg? Behind the curtain of our everyday perceptions lie theories so mind-bending, they upend everything we assume to be true. Some suggest we're living in a simulation, an intricate digital construct created by an advanced civilization. Others propose that time isn't linear at all, but a vast, tangled web where past, present, and future exist simultaneously. And then there are the ideas that challenge the very fabric of space itself, hinting that multiple universes might be stacked like pages in a book, each with its own version of you, making different choices, living different lives. Today, we're diving deep into 30 of the most fascinating theories about the nature of reality, each one a doorway into a world more extraordinary than the last. These aren't just abstract concepts, they're clues that could rewrite our understanding of existence, from the quantum realm where particles defy logic to the edges of cosmology, where the universe might be a hologram projected from a distant boundary. We'll explore ideas that blur the line between science and philosophy. So buckle up, because by the end of this journey, you might never look at the world the same way again. Could reality be nothing more than an incredibly complex video game? That's the startling premise behind simulation theory, the idea that everything we perceive, our bodies, the stars, even the passage of time, might be an artificial construct, lines of code in a hyper-realistic simulation designed by an advanced civilization. Think of it like this: if humanity keeps advancing technologically, someday we might create simulations so detailed, the beings inside them believe they're real. Now, what if we're already inside one of those simulations? Philosopher Nick Bostrom laid out a compelling case for this with his famous trilemma. He argued that at least one of these statements must be true. Either nearly all civilizations go extinct before reaching simulation-capable technology, or advanced civilizations lose interest in creating ancestor simulations, or we're almost certainly living in one right now. Since the first two options seem unlikely given humanity's relentless curiosity, the third becomes disturbingly plausible. Even figures like Elon Musk have pointed out the statistical odds. If simulations outnumber base reality, the chances we're in the real world shrink to almost zero. But how could we test such a radical idea? Some scientists suggest looking for glitches, tiny errors in the fabric of reality that might reveal the code beneath. Imagine spotting a gravitational anomaly where the rules of physics seem to stutter, or catching a flicker in cosmic background radiation like a pixelated corner of a digital universe. Others propose quantum experiments to detect potential computational limits, like the universe rendering details only when observed, just as a video game loads graphics to save processing power. The implications are dizzying. If simulation theory holds, our entire history, our struggles and triumphs, could be someone else's experiment or entertainment. Yet rather than diminish our existence, this idea might make it even more extraordinary, proof that consciousness, in any form, is the ultimate miracle. What if our universe, with all its vast galaxies and swirling nebulae, is actually a flat, two-dimensional surface that only appears three-dimensional, like a hologram? This isn't science fiction, it's a legitimate scientific hypothesis known as the holographic principle, and it could rewrite our understanding of reality itself. The idea stems from one of the strangest puzzles in physics. When matter falls into a black hole, what happens to all the information it contains? quantum mechanics says information can't be destroyed, but black holes seem to erase it completely. Leonard Susskind and physicist Gerard T. Hooft proposed a radical solution: the information isn't lost. Instead, it's smeared across the black hole's event horizon, the boundary where nothing, not even light, can escape. Think of it like a movie projected onto a screen. The images appear three-dimensional with depth and movement, but they're actually encoded on a flat surface. In the same way, our universe might be a cosmic projection, with everything we see, touch, and experience, every star, every atom, even our own consciousness, encoded on a distant, two-dimensional boundary we can't perceive. This would mean that solid matter, the stuff that feels so real beneath our fingertips, is just an illusion, a kind of cosmic trick of the light. The implications are staggering. If the holographic principle is correct, it could unite two of physics' greatest theories, quantum mechanics and general relativity, into a single framework. It would mean that space isn't smooth and continuous but pixelated, like a digital image, with a fundamental limit to how small those pixels can be. Experiments at Fermilab and other facilities are already searching for evidence of this pixelation in the fabric of spacetime, looking for subtle blurring in high-energy particles that might reveal the underlying code. Even more mind-bending is what this says about free will and perception. If reality is a projection, are our choices truly ours, or are they written in advance on that distant boundary? And if the universe is fundamentally two-dimensional, what does that make us? Just shadows dancing on the wall of a higher dimensional world? The holographic principle doesn't just challenge our understanding of physics, it forces us to question what it means to exist at all. What if every choice you've ever made, every path taken or not taken, exists somewhere in an endless sea of parallel realities? Multiverse theory suggests our universe might be just one of countless others, each with its own version of history, physics, and even you. This isn't a single idea but a web of concepts, each offering a different twist on how these alternate realities might form. One of the most compelling versions comes from cosmic inflation, the idea that our universe rapidly expanded in its earliest moments. Some physicists, like Alan Guth, propose this expansion never truly stopped. Instead, it continues eternally in some regions, spawning new bubble universes like froth in an infinite ocean. Each bubble could have entirely different laws of physics, perhaps one where gravity is stronger, or light moves slower, or even where time runs backward. The sheer variety is unimaginable, raising a haunting question. Is our universe's delicate balance of physical constants just a lucky accident, or are we one of countless experiments in a cosmic lab? Then there's the quantum many worlds interpretation, where every possible outcome of every event actually happens. When you flip a coin, the universe doesn't choose heads or tails, it splits, creating two branches where both results exist. Over a lifetime, those branches multiply into infinity, meaning there's a version of you who became an astronaut, another who moved to a different country, and countless others who made choices you never even considered. The math behind this is eerily robust, solving puzzles about how particles behave in superposition. But it also forces us to ask, if every possibility is realized somewhere, what does that mean for free will or even the concept of identity? These theories aren't just thought experiments, they solve real cosmological headaches. The multiverse could explain why our universe seems oddly fine-tuned for life, a question that keeps physicists awake at night. If there are infinite universes with random physical laws, it's no surprise we find ourselves in one where conditions allow us to exist, but the philosophical toll is heavy. If every tragedy is counterbalanced by a version of reality where it didn't happen, does suffering lose its meaning? And if there are infinite versions of you, is any single life truly significant? Some scientists push back, arguing the multiverse is untestable, more metaphysics than physics. But others hunt for evidence in the cosmic microwave background, searching for imprints of collisions between bubble universes. Whether proven or not, these ideas stretch our imagination to the breaking point, revealing a reality far stranger and more vast than we ever dreamed. Now, let's explore one of the most unsettling ideas in modern cosmology, Boltzmann brains. Picture this: floating in the infinite void of space, a fully formed, conscious mind suddenly flickers into existence, complete with memories, thoughts, and the illusion of a past, only to vanish just as quickly. No body, no universe, just a lone, self-aware entity conjured from pure chaos. This isn't a scene from a sci-fi nightmare. It's a legitimate thought experiment that challenges our understanding of reality's origins. The idea traces back to 19th century physicist Ludwig Boltzmann, who suggested that if the universe lasts long enough, random fluctuations in a sea of entropy could, by sheer chance, create order from disorder. Given infinite time, even the most improbable events become inevitable, including the spontaneous formation of a thinking mind. Here's the disturbing twist: statistically, it's far more likely for a single, isolated brain to pop into existence than for an entire ordered universe like ours to emerge. After all, crafting one self-aware moment requires vastly less energy and organization than building galaxies, planets, and billions of years of cosmic history. This leads to a paradox that keeps cosmologists up at night. If our universe is eternal or cyclical, as some theories suggest, then Boltzmann brains should vastly outnumber ordinary, evolved minds like ours. So why don't we experience reality as fleeting, disconnected flashes of consciousness? Why does the world feel so stable and continuous? Some physicists argue this implies our universe isn't eternal, that it had a definite beginning like the Big Bang, which prevents the infinite time required for Boltzmann brains to dominate. Others see it as a fatal flaw in certain models of quantum gravity or the multiverse, forcing scientists to rethink fundamental assumptions. The implications ripple into philosophy. If reality is teeming with these disembodied minds, how could we ever trust our own memories or observations? What if you are a Boltzmann brain, hallucinating this very moment before dissolving back into the void? While the idea feels absurd, it's a serious stress test for cosmology, exposing gaps in our theories. It reminds us that the universe, for all its apparent order, might rest on foundations far stranger and more precarious than we dare admit. What if the universe isn't just governed by physical laws but by lines of code? Digital physics flips our understanding of reality on its head, proposing that the cosmos operates like an unimaginably vast quantum computer, with every particle, every force, even time itself unfolding as part of a grand computation. At its core, this theory suggests that information isn't just a way we describe the universe, it's the fundamental fabric from which reality is woven. Pioneers like Edward Fredkin and Stephen Wolfram have championed this mind-bending perspective. Fredkin argued that the universe is fundamentally digital, built from discrete bits of information that interact according to simple computational rules. Think of it like chess. The board and pieces may seem physical, but the real magic happens in the abstract rules governing their movements. In the same way, the swirling galaxies and subatomic particles we observe might just be the visible outputs of an invisible program running beneath the surface. Wolfram took this further with his idea of cellular automata as simple programs that generate incredibly complex patterns, almost like digital universes in miniature. He suggests our own cosmos could emerge from similar computational building blocks, where even randomness and chaos are just features of the code. But how could something as intangible as information create the solid world we experience? Imagine a video game rendering a forest in real time. The trees, the wind, the sunlight, none of it is real in the traditional sense, yet the rules of the software make it feel tangible to the player. Digital physics proposes our universe might work the same way, with physical laws acting as algorithms that process information into what we perceive as matter, energy, and motion. Even quantum weirdness, like particles being in two places at once, could simply be the system handling multiple calculations simultaneously. The implications stretch beyond theory. If the universe is computational, there might be limits to its processing power, a cosmic resolution where reality becomes pixelated at the smallest scales. Some researchers speculate this could explain mysteries like why empty space still crackles with quantum energy, or why time seems to flow in one direction. Others wonder if we might someday uncover the universe's source code, revealing hidden commands that govern everything from gravity to consciousness. Critics argue digital physics risks being untestable, more philosophy than hard science, but supporters counter that clues might lurk in the fine structure of spacetime or the behavior of entangled particles. Whether proven or not, this theory forces us to reconsider what reality truly is. Not a collection of objects, but a dynamic, ever-unfolding computation where we're not just observers, but active participants in the processing. What if everything you see, touch, and experience is an elaborate illusion? Not because reality is a simulation, but because your own mind designed it that way. This is the radical proposition of conscious realism, a theory that flips traditional physics on its head. Cognitive scientist Donald Hoffman doesn't just argue that space-time and matter might be secondary. He claims they're more like a user interface, a simplified dashboard your brain creates to help you navigate a reality far stranger than you perceive. Hoffman's starting point is evolution. For centuries, we've assumed our senses give us an accurate picture of the world, that a tree looks like a tree because it is a tree. But Hoffman points out evolution doesn't care about truth, it cares about survival. Imagine a prehistoric human sees a snake. The brain doesn't need to know the quantum makeup of the snake's scales, it just needs to scream danger and trigger a leap backward. Over millions of years, our perceptions evolved not to show us reality as it is, but to hide the overwhelming complexity beneath a simplified, survival-friendly illusion. Think of it like a computer desktop. The trash icon isn't literally a tiny bin, it's a symbolic representation of something far more complex happening in the machine's code. This leads to Hoffman's explosive conclusion: space-time itself is part of the illusion. Just as the desktop's icons and folders don't exist inside the computer's hardware, the physical world we perceive might not exist outside our conscious experience. Instead, Hoffman proposes that reality is fundamentally a vast network of conscious agents, not just humans or animals, but irreducible units of awareness interacting in ways we can't yet fathom. In this view, a rock isn't a collection of atoms, it's a pattern of interaction between these deeper conscious entities, appearing solid only because that's how our interface renders it. The implications are staggering. If Hoffman's right, then quantum mechanics' famous observer effect, where particles seem to choose a state only when measured, isn't a quirk of physics but a clue that consciousness comes first. Even time and space might dissolve at this deeper level, meaning what we experience as the past, present, and future could be like separate windows open on a cosmic desktop, all running simultaneously. Critics argue this sounds like solipsism wrapped in scientific jargon, a fancy way of saying nothing is real. But Hoffman's team uses mathematical models to show how networks of conscious agents could generate phenomena resembling spacetime, offering testable predictions. Some experiments even suggest our perceptions might encode far less information about objective reality than we assume, as if the brain actively obscures the truth to keep us functional. Whether proven or not, conscious realism forces us to ask, if reality is nothing like what we perceive, what else might be lurking just beyond the edges of our interface? We all live by the tick of the clock, watching seconds turn to minutes, birthdays pass, seasons change. But what if time, that relentless river carrying us forward, isn't real at all? Physicists like Julian Barber argue that time might be nothing more than a convincing illusion, a trick played on us by the way our brains stitch together moments. Imagine a film strip. Each frame exists independently, but when played in sequence, it creates the illusion of motion. Barber suggests reality works the same way. What we call time is just a series of frozen snapshots or nows arranged in a way that gives the impression of flow. Without memory, would we even notice the difference? This radical idea isn't just philosophy, it's grounded in equations. The Wheeler-DeWitt equation, a cornerstone of quantum gravity, describes the universe without any reference to time at all. When physicists tried to combine Einstein's relativity with quantum mechanics, time simply vanished from the math. Like discovering that a familiar landscape is actually a reflection in a mirror, the equations hint that time might emerge from something deeper, the way temperature emerges from the chaos of countless molecules. Quantum gravity theories like loop quantum gravity and string theory take this further, suggesting time could be a side effect of how entangled particles relate to one another, a cosmic network of connections masquerading as sequence. Think of it like watching a crowd at a stadium do the wave. From a distance, you see a ripple moving around the stands, but there's no actual thing traveling. It's just thousands of people standing and sitting in a coordinated pattern. Similarly, time's arrow, why we remember the past but not the future, might arise from increasing disorder in quantum relationships, not some intrinsic flow. Experiments with supercooled atoms even show particles behaving as if time is irrelevant, with cause and effect blurring into symmetry. The implications unravel our most basic assumptions. If time isn't fundamental, does now have any meaning beyond human perception? Could the past and future exist simultaneously, like pages in a book we're reading one chapter at a time? And if so, who or what is turning the pages? What if numbers and equations weren't just tools to describe reality? What if they were reality? This is the bold claim at the heart of the mathematical universe hypothesis proposed by physicist Max Tegmark. He suggests our cosmos isn't just governed by math. It is math, a vast, self-contained mathematical structure. Not an approximation, not a model, but pure mathematics in its most literal form. Think of it like this: when we study a circle in geometry, we're exploring an abstract idea, a set of points equidistant from a center. But Tegmark argues there's no fundamental difference between that abstract circle and the shape of a planet orbiting a star. Both are manifestations of the same underlying mathematical truth. In this view, the universe isn't made of particles or waves, but of numbers and relationships, with everything from gravity to consciousness emerging from equations playing out in an infinite cosmic computation. This idea tackles one of physics' great mysteries: why math works so uncannily well in describing nature. Einstein called it the unreasonable effectiveness of mathematics. From predicting antimatter to black holes, math often reveals reality's secrets before experiments confirm them. If the universe is inherently mathematical, that effectiveness isn't a lucky accident, it's the only possible outcome. The equations aren't describing reality, they're constructing it, like lines of code generating a virtual world. Tegmark takes this further by classifying possible mathematical universes into 4 levels. The first is the familiar world of physics, where matter obeys equations we've discovered. The second introduces other physical laws, universes where gravity repels or light travels slower. The third embraces every possible quantum outcome, branching into infinite realities. But the fourth level is the most radical. Every conceivable mathematical structure exists as a physical reality somewhere, from the simplest geometric shapes to unimaginable dimensions beyond spacetime. Critics argue this blurs the line between science and metaphysics. How could we ever test whether the number 7 exists independently? Yet supporters point to theories like string theory, where the math predicts realities we can't yet observe. If future experiments confirm these predictions, it might hint that math isn't just a language but the foundation of existence itself. Whether proven or not, the mathematical universe hypothesis forces us to reconsider what's truly real, not atoms or energy, but the timeless, invisible relationships that weave them together. What if consciousness isn't something the brain produces, but something the universe is? Panpsychism, an ancient idea now resurfacing in modern physics, flips the traditional view on its head, proposing that awareness isn't confined to living things but is woven into the fabric of reality itself. Think of it like this: just as gravity or electromagnetism are fundamental forces, consciousness might be a basic feature of matter, not emerging from complexity, but present in some form even at the level of atoms and particles. This isn't just philosophical speculation. The hard problem of consciousness, coined by David Chalmers, asks why and how physical processes in the brain give rise to subjective experience. Why does the firing of neurons feel like anything at all? Materialist science struggles to explain this, but panpsychism offers a radical solution, because experience is elemental, like space or time. Even the simplest systems might possess a faint glimmer of awareness, what philosophers call proto-consciousness. When these systems combine in structures as intricate as a human brain, that flicker amplifies into the rich inner world we recognize as thought, emotion, and selfhood. Quantum physics adds unexpected weight to this idea. Experiments show particles behaving differently when observed, as if aware of being measured. The Orch theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests microtubules in brain cells might harness quantum processes to generate consciousness, implying that quantum vibrations present everywhere could hint at a universal substrate of awareness. Even information theory chimes in. If reality is fundamentally computational, as some theories suggest, then consciousness might be how information feels from the inside. The implications are profound. If panpsychism holds, then a star isn't just a ball of plasma, it's a slow, cosmic mind. A river's flow carries not just water, but whispers of experience. Critics argue this risks anthropomorphizing nature, but supporters counter that it's more elegant than magicking consciousness into existence solely from dead matter. It also raises haunting questions. Could AI ever truly feel? Or is it just mimicking awareness? And if consciousness is universal, what does that mean for our ethical relationship with the world around us? Panpsychism doesn't just bridge science and philosophy, it reenchants the universe, suggesting that every particle, every galaxy, hums with an inner life we're only beginning to understand. Imagine the universe not as a smooth, continuous fabric, but as a patchwork of microscopic geometric shapes, tiny triangles stitching together the very structure of spacetime itself. This is the essence of causal dynamical triangulation, a bold approach to quantum gravity that suggests our four-dimensional reality might emerge from something far simpler, a cosmic Lego set of basic building blocks. Unlike string theory's tiny vibrating threads or loop quantum gravity's networks of spin, this theory takes a radically geometric view where reality arises from the way these elemental shapes connect. The idea begins with a puzzle Einstein's relativity can't solve. What happens to spacetime at the smallest scales? General relativity paints gravity as the bending of smooth spacetime, but quantum mechanics insists everything becomes grainy at the tiniest levels. Causal dynamical triangulation bridges this divide by proposing that spacetime isn't fundamental, it's assembled from triangular pieces called simplices, each a tiny chunk of geometry with built-in causality to ensure time always moves forward. Picture a stop-motion animation where each frame is a static 3D shape, but played in sequence, they create the illusion of motion. Here, the frames are these simplices, and the animation is the universe we experience. What's astonishing is how complex behavior emerges from such simple rules. When physicists run computer simulations connecting millions of these simplices with strict causality links, something remarkable happens. At large scales, the chaotic jumble spontaneously organizes into the four-dimensional spacetime we recognize, complete with familiar properties like gravity and an arrow of time. It's as if the universe computes its own structure from the bottom up, with no top-down blueprint required. Some models even reproduce Einstein's equations as a natural consequence, hinting that relativity might be an emergent phenomenon, not a fundamental law. This theory also offers clues about the Big Bang. In simulations, if you rewind the triangulation backward, spacetime doesn't collapse to a singularity. It transitions into a pre-geometric phase where dimensions lose meaning. This suggests the birth of our universe might not have been a violent explosion from nothing, but a phase change like ice melting into water, where time and space crystallized from something more primitive. Critics argue the approach is too abstract, lacking experimental predictions we can test. Yet supporters counter that its simplicity is its strength, a universe built from geometric first principles, where complexity arises from the bottom up, might finally reconcile quantum weirdness with cosmic order. Whether proven or not, causal dynamical triangulation reshapes our view of reality, revealing a cosmos that isn't handed to us fully formed, but one that assembles itself piece by piece from the humblest of parts. String theory often steals the spotlight in the search for quantum gravity. But what if the answer lies not in tiny vibrating strings, but in the very fabric of spacetime itself? Loop quantum gravity offers a radically different vision, one where space isn't smooth and continuous, but made of indivisible grains like pixels on a cosmic screen. Imagine zooming in on the surface of a pond until the water's smoothness shatters into individual molecules. Loop quantum gravity suggests spacetime does the same at the smallest possible scale. The Planck length, a distance so tiny, 1,000,000 billion of them could fit across a single atom. At this level, gravity isn't a force bending spacetime. It is spacetime woven from intricate networks of spin foams. Picture a vast, ever-changing web where each thread represents a quantum of area or volume, carrying information about how spacetime curves and twists. These threads intersect at nodes, creating what physicists call spin networks, abstract mathematical structures that encode the geometry of the universe itself. It's like reality is a cosmic tapestry, with every knot and connection determining how matter moves and time flows. Unlike string theory's extra dimensions, loop quantum gravity keeps it simple, just the four dimensions we know, but fundamentally pixelated. The theory's most startling prediction, space can't be divided infinitely. Just as you can't split an atom without changing its nature, spacetime itself has a smallest possible unit, a quantum of space about 10 to the minus 35 meters across. This granularity might explain why black holes don't crush matter into infinitely dense points, but instead halt collapse at this fundamental scale. Even the Big Bang might not have been a singularity, but a bounce, where a previous universe collapsed to this tiny size before rebounding into our expanding cosmos. Critics argue the theory struggles to explain how smooth spacetime emerges from these discrete building blocks at larger scales, like how a digital photo appears seamless from a distance. Yet recent simulations show spin networks spontaneously organizing into familiar four-dimensional spacetime, hinting at a profound truth. The universe might not have a stage, it is the stage, constantly weaving itself into existence. Whether loop quantum gravity ultimately unites relativity and quantum mechanics or not, it forces us to rethink reality's deepest foundations not as a backdrop to physics, but as its most dynamic player. String theory promised to be the theory of everything, uniting gravity and quantum mechanics under one elegant framework, tiny vibrating strings whose harmonies composed all particles and forces. But as physicists dug deeper, they uncovered a staggering twist. Instead of one unique solution, string theory allows for an estimated 10 to the 500 possible configurations, a number so vast it dwarfs the atoms in the observable universe. This is the string theory landscape, a cosmic maze where every turn leads to a different version of reality, each with its own laws of physics, dimensions, and fundamental constants. At the heart of this labyrinth lies the vacuum state, the lowest energy configuration of a universe, like the calmest setting on a cosmic dial. In string theory, the way extra dimensions curl and twist determines these states, meaning slight changes could produce universes where gravity is stronger, light moves slower, or chemistry as we know it is impossible. This raises a profound question. If most of these universes are inhospitable to life, why does ours seem so finely tuned? Enter the anthropic principle, the idea that we observe this particular universe simply because its conditions allow us to exist. It's like winning a cosmic lottery where the prize is consciousness itself, a lottery with 10 to the 500 tickets, and nearly all of them are duds. Critics argue this approach borders on metaphysics. Nobel laureate Sheldon Glashow compared it to medieval epicycles, adding complexities to preserve a theory rather than letting evidence guide it. If string theory permits every possible outcome, how could we ever falsify it? Others counter that the landscape might be inevitable. Just as Darwin's theory of evolution explains life's diversity through random mutation and selection, the multiverse could explain physics' fine-tuning through sheer probability. After all, in an infinite array of universes, even the most improbable outcomes must occur somewhere. The debate cuts to the core of science's purpose. Is physics about finding a single, beautiful equation that explains everything, or is it about mapping the branches of reality's tree, no matter how tangled they grow? Some theorists seek a deeper principle that might trim the landscape, while others embrace its vastness as a feature, not a bug. For now, the string theory landscape remains both a dazzling possibility and a cautionary tale, a reminder that even our grandest theories might be just one verse in a much stranger cosmic poem. What if gravity, the force that holds planets in orbit and keeps our feet on the ground, isn't a fundamental force at all, but something far stranger? Physicist Eric Verland stunned the scientific world with a theory as bold as it is elegant. Gravity might not be one of the universe's basic building blocks, but an emergent phenomenon, a side effect of a deeper, invisible dance happening at the fabric of reality. Think of it like the way temperature emerges from the motion of atoms. You can't point to a single molecule and say, "There's the heat," yet collectively they create something entirely new. Verland argues gravity works the same way, arising not from particles or fields, but from something even more fundamental, information. His starting point is entropy, a measure of disorder that, surprisingly, might hold the key to gravity's mystery. In thermodynamics, systems naturally evolve toward higher entropy, like a drop of ink dispersing in water. But in the 1990s, physicist Ted Jacobson showed that Einstein's equations of general relativity could be derived from thermodynamic principles, hinting that spacetime itself might behave like a sort of cosmic heat engine. Verland took this further, proposing that gravity is what happens when the universe tries to maximize entropy, rearranging itself like a deck of cards shuffling toward chaos. When matter distorts spacetime, it's not because of some invisible force, it's because the underlying bits of reality, the ones storing information about where things are, naturally shift to accommodate this disorder. The implications are profound. If Verland's right, it could solve one of cosmology's biggest headaches, dark matter. Astronomers observe galaxies rotating so fast they should fling themselves apart, yet something invisible holds them together. Dark matter was proposed as the glue, but despite decades of searching, no one's found it. Emergent gravity offers a radical alternative. Maybe the extra gravitational pull isn't from unseen matter at all, but from the way information entropy interacts on cosmic scales. In this view, dark matter is an illusion, a mirage created by our misunderstanding of gravity's true nature. Some galaxies' rotation curves already match Verland's predictions eerily well without invoking mysterious particles. This theory also ties back to the holographic principle, the idea that our three-dimensional reality might be a projection of information stored on a two-dimensional surface. If gravity emerges from entropy, and entropy is fundamentally about information, then gravity itself becomes a kind of cosmic data processing, a way the universe updates its state. Critics argue the math isn't yet precise enough to replace dark matter entirely, and lab experiments remain inconclusive. But Verlaine's vision reframes our place in the cosmos, not as observers standing outside the laws of physics, but as participants in a vast, unfolding computation where even the pull of a star might be nothing more than the universe's way of keeping its books balanced. Every time you open your eyes, the world seems sharp and definite. A chair is here, a table is there, each object firmly in place. But quantum mechanics tells a far weirder story. Until observed, particles exist in smeared-out superpositions everywhere and nowhere at once. So how does the fuzzy quantum realm give rise to the solid, unambiguous reality we experience? Enter quantum Darwinism, a theory that doesn't just solve this mystery, it rewrites our understanding of how reality crystallizes from possibility. At the heart of this idea is the measurement problem, one of quantum mechanics' deepest puzzles. Why do particles seem to choose a definite state only when measured? Early interpretations pointed to consciousness or wave function collapse, but quantum Darwinism takes a radically different approach. What if classical reality emerges through a kind of quantum natural selection, where only the most stable information survives? Think of it like a game of whispers. When one person tells a secret to another, details get distorted or lost. But if that secret spreads to hundreds of people, certain consistent elements stick while noise fades away. In the quantum world, interactions with the environment, air molecules, light particles, even cosmic background radiation act like those gossipers, constantly measuring quantum systems by scattering information about them. This process, called decoherence, isn't random. Some quantum states are more robust, more easily copied and spread by the environment without getting scrambled. Over countless interactions, these fittest states proliferate, while fragile superpositions vanish like whispers drowned out by a crowd. The result: what we perceive as objective reality isn't a single observation magically collapsing possibilities. It's the consensus emerging from trillions of tiny natural measurements. Your coffee cup appears stationary not because you looked at it, but because its position has been redundantly imprinted on photons, air currents, and dust particles, creating a stable classical signature. The implications stretch beyond philosophy. Quantum Darwinism explains why we never see macroscopic objects in superpositions. Their states are constantly being broadcast and reinforced by the environment, leaving no room for quantum weirdness at human scales. It also sidesteps the need for consciousness to play any special role in reality's formation. The universe doesn't care if a human, a camera, or a rock observes. A particle decoherence happens either way, driven by pure physics. Critics argue the theory doesn't fully explain why certain states are selected over others or how subjective experience fits in, yet experiments are already lending support. In labs, researchers can track how quantum information spreads into the environment, mirroring the redundancy quantum Darwinism predicts. Some even suggest this could revolutionize quantum computing, showing us how to protect fragile superpositions from decoherence by controlling their information leaks. Most stunning is what this says about reality's nature. The solid world we take for granted might be more like a hologram, its apparent objectivity just the echo of countless quantum interactions. In this view, the universe isn't a cold, mechanical clockwork. It's a dynamic network of information where what we call real is simply the data durable enough to endure. Most physics theories focus on predicting what will happen. A ball rolls downhill because gravity pulls it, an atom decays at a certain probability. But what if we flip the script entirely? Constructor theory, pioneered by physicist Chiara Marletto, asks a radically different question, not what occurs but what's possible in the first place. Imagine reality as a vast game with rules that don't describe movement, but define what moves are even allowed. This isn't just philosophy, it's a mathematical framework that could bridge the gap between quantum weirdness and classical certainty while revealing deeper truths about information itself. At its core, constructor theory replaces traditional equations with a binary language of transformations. Instead of tracking particles' paths, it categorizes processes as either possible or impossible under physical law. Think of it like the rules of chess. You don't predict where a knight will move next, but you know it can't jump in a straight line. Similarly, Marletto's approach distills physics into principles about what can or can't be constructed, hence the name. A simple example, perpetual motion machines aren't just impractical, they're impossible transformations ruled out by the laws of thermodynamics. This shift in perspective might seem subtle, but it's like swapping a roadmap for a terrain model. Suddenly, hidden features of reality snap into focus. One stunning application is unification. Quantum mechanics and general relativity clash because they describe the world in incompatible languages, one probabilistic, the other deterministic. Constructor theory speaks both. For instance, it frames quantum superposition not as a particle being here and there, but as a possible transformation where information about position remains open until interaction. Likewise, spacetime curvature in relativity becomes a constraint on what transformations can occur near mass. By focusing on these meta-rules, constructor theory sidesteps the need to reconcile equations directly, offering a Rosetta Stone for physics' greatest divide. Where it gets truly mind-bending is its treatment of information. In traditional physics, information is a side effect, a description of states. But Marletto argues it's fundamental, with reality's building blocks being information transformations. Consider a quantum bit. Its ability to exist in multiple states at once isn't just a quirk, it's a possible transformation that classical bits can't achieve. Constructor theory treats this distinction as foundational, suggesting that the universe's deepest laws might be about what information can be copied, erased, or preserved. Some even speculate this could explain why time flows forward. Certain information processes are irreversible by their very nature. Critics argue the theory is still more framework than formula, lacking experimental predictions. Yet its power lies in generality. It's already inspired new approaches to thermodynamics, showing how heat engines' limits emerge from deeper impossibility principles. Others use it to explore self-replicating machines not as sci-fi, but as theoretical constructs obeying or defying transformation laws. Whether it revolutionizes physics or not, constructor theory challenges us to see reality not as a clockwork of causes and effects, but as a cosmic rulebook where the very concept of can and can't might hold the keys to existence. The quantum world is a place of ghostly possibilities, particles existing in multiple states at once, spread out like ripples in a pond until suddenly, inexplicably, they snap into sharp focus. Most interpretations, like the famous Copenhagen view, say this collapse into definiteness happens when we observe or measure a system. But what if reality doesn't need an observer at all? Objective collapse theories propose a radical alternative. Wave functions collapse on their own, spontaneously and randomly, as if the universe itself gets tired of indecision. The most famous of these models is the Guerradi-Rimini-Weber theory, or GRW. Picture a quantum particle like an electron. Under normal quantum rules, it can hover in a superposition, say, spinning both clockwise and counterclockwise at once. But GRW introduces a tiny, inherent instability. Every now and then, the particle's wave function suddenly jumps, snapping to one state or the other. It's not because anyone looked, it's just how reality works, like a flipped coin finally landing. For a single particle, this collapse might take billions of years. But for a macroscopic object made of trillions upon trillions of particles, the chances multiply, meaning collapses happen constantly, keeping everyday objects firmly in one place. This solves one of quantum mechanics' biggest headaches, the measurement problem. Copenhagen relies on a vague boundary between quantum and classical, where observation somehow forces definiteness. GRW cuts through the mystery by making collapse a physical process, as natural as radioactive decay. There's no need for conscious observers or magical lines between small and large, just a universe that occasionally nudges itself toward clarity. But how could we test such an idea? If collapses are real, they'd release minuscule amounts of energy as wave functions snap. Experiments like those at the Gran Sasso Laboratory in Italy hunt for these faint bursts in ultra-cold crystals, where even a tiny energy ripple could betray spontaneous collapse. Other proposals suggest monitoring large molecules in superpositions. If GRW is correct, they'd collapse faster than standard quantum physics predicts, as if reality has a built-in timer for resolving ambiguity. Critics argue these theories add unnecessary complexity, inventing new physics to dodge philosophical discomfort. Yet supporters counter that GRW's collapses might explain why we never see cats both dead and alive in real life, even if Schrödinger's famous thought experiment allows it mathematically. The debate isn't just academic. If objective collapse is real, it could reshape technologies like quantum computing, where maintaining superpositions is key. At its heart, this idea challenges our place in the universe. If reality solidifies without us, then consciousness isn't a privileged player, just a bystander in a cosmos that crystallizes all on its own. Whether GRW or similar models hold up, they remind us that quantum mechanics might be even stranger and more independent than we ever imagined. What if quantum particles could send signals not just through space but through time itself? That's the wild premise of the transactional interpretation, a quantum theory where the present moment isn't just shaped by the past, it's also influenced by echoes from the future. Picture two people trying to agree on where to meet for dinner. One sends out proposals, "How about pizza?" while the other responds with confirmations, "Only if it's pepperoni." In this quantum version, particles behave similarly but with a twist. Their negotiations span across time, weaving the fabric of reality through a dance of waves traveling both forward and backward. Here's how it works. When a quantum event occurs, say, an electron deciding where to land on a detector, it doesn't just take a single path. According to physicist John Cramer, the electron emits an alpha wave that ripples forward in time, exploring all possible routes. But here's the kicker. The detector then sends a confirmation wave backward in time, selectively reinforcing the paths that align with the eventual outcome. It's as if the future reaches back to sculpt the past, ensuring everything snaps into place consistently. This handshake across time, called a transaction, resolves one of quantum mechanics' biggest puzzles: why particles seem to know where they're supposed to end up, even when taking every possible path at once. The implications are dizzying. This interpretation elegantly explains the famous double-slit experiment, where particles act like waves when unobserved but snap into particle-like positions when measured. In the transactional view, the act of measurement isn't magical. It's simply the moment when the backward confirming waves lock in, finalizing the deal between emitter and absorber. Even spooky action at a distance, where entangled particles instantly coordinate their states, becomes clearer. Their offer and confirmation waves are already entangled across time, like pen pals exchanging letters before the envelopes are even sealed. But the weirdness doesn't stop there. If transactions involve waves from the future, does that mean reality is fundamentally non-causal? Not quite. The math ensures these temporal loops are self-consistent. No grandfather paradoxes allowed. Think of it like a movie script getting revised collaboratively. The ending might influence the opening scene, but by the time filming starts, every detail fits seamlessly. Some physicists argue this could even explain quantum randomness. The choice of which transaction completes might be the universe's way of balancing its cosmic checkbook, ensuring energy and information flow smoothly across time. Critics dismiss this as a clever metaphor without experimental teeth, but supporters point to delayed choice experiments where altering detector settings after a particle's journey seems to retroactively change its behavior. Whether the transactional interpretation ultimately holds up or not, it forces us to confront a radical possibility. Time might not be the one-way street we perceive, but a tangled web of negotiations where past, present, and future are constantly rewriting each other's rules. Quantum mechanics thrives on randomness, the idea that particles have genuine freedom in how they behave until measured. But what if that freedom is just an elaborate illusion? Superdeterminism dares to suggest that every measurement, every so-called choice a particle makes, was predetermined from the dawn of the universe, locked into place by hidden threads of cause and effect we can't perceive. In this view, the famous, spooky action at a distance that troubled Einstein isn't a mystery. It's simply the result of everything being conspiratorially connected from the start. At the heart of this idea is a brutal simplicity. If the universe is fully deterministic, then correlations between entangled particles aren't evidence of instantaneous communication. Instead, they're like two dancers who have rehearsed their routine so thoroughly, no signals are needed to stay in sync. Even the experimenter's decision to measure a particle's spin isn't truly free. It's the inevitable outcome of a causal chain stretching back to the Big Bang. Superdeterminism doesn't just solve quantum non-locality, it dissolves it entirely, revealing what we thought was randomness as the cold, mechanical unfolding of a script written long ago. Yet this elegant solution comes at a staggering cost, the death of free will as anything more than a convincing mirage. If every action, every thought is predestined by initial conditions, then even your skepticism about this very idea was determined billions of years ago. Some physicists, like Nobel laureate Gerard T. Hooft, embrace this ruthlessly logical framework, arguing it's the price of a universe without paradoxes. Others recoil not just on philosophical grounds but scientific ones. Critics argue superdeterminism is unfalsifiable, a theory that explains everything but predicts nothing unique. If all apparent randomness is really hidden determinism, how could we ever design an experiment to prove otherwise? There's a deeper unease too. Science thrives on the assumption that experimenters can make free choices about what to measure, independent of the systems they study. Superdeterminism violates this sacred principle, suggesting the universe rigs experiments in advance to hide its deterministic core. Imagine flipping a coin 1,000 times and getting heads every time, not because the coin is biased, but because some invisible force predetermined your choice to flip it. This conspiratorial flavor makes many physicists deeply uncomfortable, as if the cosmos is gaslighting us. Still, the theory lingers in academia's shadows, not because it's easily dismissed, but because it's too unsettling to ignore. Some researchers hunt for subtle signatures, patterns in quantum data that might betray a deterministic undercurrent. Others explore hybrid models where determinism governs some scales but not others. Whether superdeterminism ultimately holds up or not, it forces us to confront a haunting question. If the price of cosmic order is the illusion of choice, would we ever want to know? What if reality isn't built from particles or waves, but from something far simpler, a cosmic grid of tiny cells, each following basic rules like pixels on an infinite screen updating in perfect synchrony? This is the essence of the cellular automaton universe theory, where the universe isn't a continuous fabric but a vast dynamic computation, unfolding one tick at a time. Imagine a universe-sized version of Conway's game of life, a grid where each cell turns on or off based on the states of its neighbors. From these rudimentary interactions, astonishing complexity emerges. Shapes that move, replicate, even behave like primitive computers. Now scale that up to reality itself, where atoms, galaxies, and consciousness might just be elaborate patterns flickering across a foundational grid. Pioneering this radical vision was computer scientist Edward Fredkin, who saw the universe not as a collection of things, but as a process, a giant computer processing information at the most fundamental level. His concept of digital physics goes beyond saying the universe can be computed. It argues the universe is computation. Every interaction, from the collision of quarks to the orbit of planets, boils down to simple, discrete operations like a cosmic algorithm running on hardware we can't yet perceive. Even time, in this view, isn't a smooth flow but a sequence of steps, like frames in a film advancing at the Planck scale, the universe's smallest possible unit of duration. The beauty of this idea lies in its economy. Just as the game of life generates intricate behavior from just 3 rules, the laws of physics might emerge from similarly minimalist code. For instance, relativity's space-time curvature could be how the grid renders gravitational interactions at larger scales, while quantum weirdness like entanglement might reflect non-local updates between distant cells. Some models even suggest that what we call energy is just the active processing of information, with particles being stable patterns that persist as the automaton iterates. But how could something so simple explain the richness of reality? Consider fractals, mathematical shapes that repeat their patterns infinitely at every scale. From a handful of rules, they generate coastlines, snowflakes, even the branching of trees. If the universe operates similarly, then the complexity we see, neural networks, ecosystems, spiral galaxies might just be epiphenomena, shimmering mirages atop a deeper digital substrate. This isn't just speculation. Researchers have shown how cellular automata can reproduce phenomena like fluid dynamics and quantum fields, hinting that nature's code might be discoverable. Critics argue this reduces reality to a sterile simulation, stripping away the tangible. Yet supporters counter that it elevates information to the ultimate currency of existence, a view increasingly echoed in quantum gravity research. After all, if a handful of rules can create a virtual universe indistinguishable from ours, why couldn't the real thing work the same way? Whether proven or not, the cellular automaton universe invites us to see existence anew, not as a static stage, but as an ongoing computation, where every moment is the universe solving for itself, one cell at a time. Time crystals sound like something ripped from a sci-fi novel, structures that move, oscillate, or even tick without ever consuming energy, defying one of physics' most sacred principles, the arrow of time. Normally, if you leave a system alone, it settles into equilibrium like a pendulum coming to rest. But time crystals flout this rule, perpetually cycling through states in their ground state, the lowest possible energy configuration, as if the universe granted them a loophole in its own laws. First proposed by Nobel laureate Frank Wilczek in 2012, these bizarre quantum systems don't just challenge our understanding of matter, they force us to reconsider what time is at the most fundamental level. The magic lies in broken symmetry. Most physical systems look the same if you shift them in space or time, rotate a snowflake, and its pattern repeats. But time crystals spontaneously break time translation symmetry, meaning their structure evolves periodically even when undisturbed, like a clock that ticks forever without winding. Imagine pushing a child on a swing. Normally, the swing slows and stops unless you keep pushing. A time crystal, though, is like a swing that keeps swinging on its own, not because it's stealing energy from somewhere, but because its quantum architecture makes motion an intrinsic property, as unavoidable as an electron spin. Creating these systems in the lab requires bending reality's rules. Researchers use chains of ions or diamond defects, entangling their quantum states and then kicking them with laser pulses. Instead of settling down, the system responds by oscillating at a fraction of the pulse frequency, a ghostly rhythm emerging from quantum cooperation. It's as if you tapped a piano key and the string vibrated at a different pitch entirely, one dictated not by energy input but by the universe's hidden metronome. These experiments confirm time crystals aren't just mathematical curiosities. They're physical phenomena, with Google's quantum processor Sycamore even simulating their behavior in 2021. Why does this matter? Time crystals hint at equilibrium. The idea that all things trend toward stillness might not be universal. Some quantum systems could resist this fate indefinitely, dancing at the edge of entropy without ever succumbing to it. On a cosmic scale, this might explain how certain structures, like black hole horizons or even space-time itself, sustain dynamic activity without obvious energy sources. More provocatively, if time crystals can remember their rhythmic states across perturbations, they could redefine how we think about quantum memory, paving the way for uncrashable computers or clocks that keep perfect time until the heat death of the universe. But the deepest implication is philosophical. Time crystals treat time not as a backdrop but as a material that can be sculpted. In Einstein's relativity, time is flexible, warped by gravity. Quantum mechanics treats it as an external parameter. Time crystals, though, suggest time might emerge from relationships between quantum components, a chorus of interactions creating the illusion of flow. If so, then the ticking of these crystals isn't just a curiosity. It's a glimpse into how the universe stitches moments into a continuum, one quantum beat at a time. Black holes aren't just cosmic vacuum cleaners, they might be cosmic wombs. Black hole cosmology flips the script on our origins, proposing that our entire universe isn't expanding into some vast, empty void, but tucked inside the singularity of a black hole belonging to a larger parent universe. This isn't just wild speculation. It's a theory that elegantly ties together some of cosmology's thorniest puzzles, from the Big Bang's initial conditions to the eerie parallels between black hole physics and holographic reality. Picture a black hole in this parent universe. As matter falls in, it doesn't just vanish, it gets crushed to infinite density at the singularity, a point where space-time curvature and known physics break down. But what if that singularity isn't an endpoint but a bridge? Theoretical models suggest the collapse could trigger a rebound, birthing an entirely new space-time domain inside the black hole, our universe. The math mirrors the Big Bang's explosive expansion with one critical difference. Instead of emerging from a mysterious singularity, from nothing, our cosmos would inherit its structure from the black hole's properties, its mass, spin, and charge. This could explain why our universe appears so finely tuned for complexity. If black holes naturally filter physical laws through their own parameters, only certain types of universes, ones with stable chemistry, gravity, and time, would emerge from the chaos. The holographic principle deepens this connection. Just as a black hole's event horizon encodes information about everything that falls in, like a cosmic hard drive, our universe might be a projection of data stored on its boundary. This could mean the three-dimensional reality we experience is just a hologram rendered from two-dimensional information imprinted on our cosmic black hole's edge. The implications are staggering. The reason the universe appears uniform and flat on large scales isn't luck, it's a consequence of being sculpted by the black hole's geometry. Even dark energy, the mysterious force accelerating cosmic expansion, might trace back to the parent black hole's gravitational influence leaking through. Critics argue this idea is untestable, a cosmic turtles all the way down scenario, but supporters point to subtle signatures that might betray our black hole origins. If our universe inherited slight asymmetries from its parent's rotation, for instance, we might find imprints in the cosmic microwave background, ghostly swirls hinting at a spin we can't otherwise detect. Others suggest that quantum fluctuations in the early universe, which seeded galaxy formation, could carry echoes of the parent black hole's quantum states. Beyond physics, this theory reshapes our existential perspective. If every black hole spawns a new universe, then reality might be an infinite fractal universes within universes, each with slightly tweaked physical laws evolving over cosmic generations. Life exists in this one not by accident, but because the black holes that birthed hospitable universes were the ones that could produce thinking beings to ponder them. Whether proven or not, black hole cosmology offers a breathtaking vision, one where the darkest objects in existence aren't just endings but beginnings, and where the answer to "where did we come from?" might lie in the heart of a forgotten abyss. We often think of time as a river carrying us inexorably from the past through the present and into the future. But what if that's just an illusion, a trick of perception? Eternalism flips this intuitive view on its head, proposing that past, present, and future aren't sequential at all, but equally real, coexisting like frames in a film strip. In this block universe, every moment from the Big Bang to the heat death of the cosmos is already out there, fixed in place like cities on a map. Your childhood, your next birthday, events you'd call yet to happen, all exist simultaneously, just as real as the words you're hearing right now. This isn't just philosophical musing, it's rooted in Einstein's relativity. His equations treat time as a fourth dimension, woven into spacetime's fabric, just like length, width, and height. Just as here and there depend on your position in space, now and then depend on your motion, two events simultaneous for one observer might happen years apart for another moving near light speed. There's no universal present that everyone agrees on, which shatters the idea of an objective flow of time. Instead, reality resembles a vast loaf of bread where each slice is a moment, and the entire loaf exists at once. This has startling implications for free will. If the future is already there, written into the block universe's structure, does choice mean anything? Some argue yes, your decisions still shape your experience, just as a character in a novel makes choices even though the book's ending is fixed. Others see eternalism as proof that freedom is an illusion, our lives predestined grooves in spacetime's geometry. The debate mirrors ancient philosophy. Stoics believed in fate but still advocated for virtue, while modern physicists like Sean Carroll suggest that even in a block universe, causality, the chain of cause and effect, remains intact. Yet eternalism also offers comfort. Loss and impermanence sting less if the past isn't gone just elsewhere in spacetime. A loved one's laughter isn't erased, it's eternally preserved in the universal block, as real as your memory of it. Even the heat death of the universe, often seen as a bleak end point, becomes just one slice in a grander, static whole. Critics argue this view feels sterile, stripping time of its dynamism. But supporters counter that it aligns perfectly with quantum mechanics, where particles seem to sense multiple timelines at once. Maybe our perception of flow is like a flashlight moving across a darkened painting. We only see one illuminated spot at a time, but the whole masterpiece has always been there. Whether eternalism is true or not, it forces us to confront a dizzying truth. The universe might not be unfolding, it might already be unfolded, with our journey through it just a matter of perspective. What if every story ever imagined, every what-if scenario, every fork in the road of history isn't just a thought experiment, but a concrete reality unfolding somewhere? Philosopher David Lewis thrust this mind-bending idea into the mainstream with modal realism, a theory so radical it redefines what real even means. Lewis didn't just suggest that other possible worlds might exist, he argued they must, with the same ontological weight as the one we call home. In this view, the universe where you became a professional skydiver or where dinosaurs never went extinct isn't fictional. It's as tangible as the screen in front of you, just causally disconnected from our own spacetime. Lewis's argument hinges on an elegant solution to age-old philosophical puzzles. Take truth claims like unicorns could have existed. Normally, we'd say this is true because unicorns don't violate any fundamental laws of nature, but what makes it true? Modal realism answers because there is a world where unicorns roam, just as real as ours, just inaccessible. Similarly, when we say, "I might have missed my train this morning," we're implicitly referencing a parallel universe where that exact scenario played out. For Lewis, these aren't just linguistic conveniences, they're evidence of a vast, branching pluriverse where every possibility is instantiated somewhere. This approach dissolves headaches like the problem of necessary beings or the nature of counterfactuals, but it comes at a cost. If all possible worlds are equally real, what makes this one special? Lewis's answer: nothing. Our universe has no privileged status, it's just the one we happen to inhabit, like a single tree in an endless forest. This levels the playing field in unsettling ways. The world where you're a Nobel Prize-winning genius exists, but so does one where every atom in your body spontaneously scatters into the void. Modal realism doesn't discriminate between the probable and the absurd. If it's logically coherent, it's out there. Critics pounce on this as extravagance gone mad. Why multiply realities beyond necessity? Lewis retorts that it's simpler to accept all possible worlds than to contrive explanations for why some seem actual while others don't. He compares it to believing in only one mountain while insisting others are possible mountains, a distinction he finds arbitrary, yet the theory's implications churn stomachs. If a world exists where suffering is maximized, does that undermine ethical meaning in ours? Lewis bites the bullet. Morality isn't about eradicating all evil across the pluriverse, an impossible task, but about making this world as just as possible. Modal realism also collides with physics. Quantum mechanics allows for probabilistic outcomes, but does every quantum branch spawn a fully fledged universe? Lewis sidesteps this, focusing on logical rather than physical possibility. His worlds don't interact or share a quantum origin. Still, the overlap with cosmological multiverse theories is tantalizing. Some physicists like Max Tegmark flirt with Lewis-like ideas, suggesting mathematical structures manifest as physical realities. Whether you find modal realism liberating or ludicrous, it forces a reckoning with our place in the grand scheme. If every possible version of you exists, is individuality an illusion? Lewis would say no, each instance is as distinct as two identical twins living separate lives. The theory doesn't diminish our reality. IT Chinese letter S the concept of existence itself into something almost too vast to comprehend. In Lewis's pluriverse, fiction becomes fact, daydreams become documentaries, and the line between here and elsewhere isn't a boundary, just an address. The human brain is often called the most complex object in the known universe, but what if its power comes not just from neurons firing, but from quantum vibrations humming deep within our cells? This is the bold claim of orchestrated objective reduction, or ORCH, or a theory forged by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They propose that consciousness isn't just an emergent property of neural complexity, it's a quantum phenomenon unfolding in tiny structures called microtubules, the skeletal scaffolding inside every brain cell. Imagine these microtubules as microscopic concert halls where quantum particles perform a symphony of superpositions and collapses, each note contributing to the melody of subjective experience. At the theory's core is a radical marriage of quantum physics and biology. Microtubules, hollow protein tubes found in neurons, are thought to process information via vibrations at the quantum scale. Penrose and Hameroff argue these vibrations create fleeting moments of quantum coherence, where particles exist in multiple states simultaneously across vast neural networks. But here's the twist. According to Penrose's earlier work on quantum gravity, these superpositions can't last forever. They eventually collapse, a process called objective reduction, and it's this collapse that generates moments of conscious awareness. In other words, every time you taste coffee or recall a memory, it might correspond to a quantum computation resolving inside your brain's architecture. Critics have pounced on Orch with ferocity. Many neuroscientists argue the brain is too warm, wet, and noisy for delicate quantum states to persist. Environmental interference would decohere them almost instantly. Others point out that microtubules exist in plants and single-celled organisms, which don't exhibit consciousness as we understand it. Even quantum physicists question whether Penrose's gravity-induced collapse mechanism holds water mathematically. And yet, intriguing clues linger. Anesthesia Hameroff's specialty works by erasing consciousness without stopping neural activity, hinting that deeper, subtler processes might be at play. Some studies even suggest microtubules can exhibit quantum-like vibrations under lab conditions, though the leap to full-blown consciousness remains speculative. If Orch were proven, the implications would rewrite reality's rules. Consciousness wouldn't be confined to brains. It might ripple through any system where quantum coherence could emerge, from mitochondria to the fabric of spacetime itself. This could bridge the infamous hard problem of how subjective experience arises from objective matter, suggesting qualia. The raw fields of experience are quantum states rendered classical through collapse. It might even explain why AI, for all its brute force processing, lacks genuine awareness. Without quantum biology, it's all hardware and no ghost. Penrose and Hameroff's theory remains controversial, straddling the line between visionary and fringe. But it dares to ask a question most neuroscience sidesteps. What if the mind isn't just a computer, but a quantum orchestra playing the universe's most mysterious tune? Whether the music holds up under scrutiny or not, Orch reminds us that consciousness might be stranger and more wondrous than we ever imagined. What if spacetime isn't smooth and continuous, but built from tiny, indivisible chunks, each one linked to the next in a vast cosmic chain of cause and effect? This is the essence of causal set theory, a radical approach that reimagines the fabric of reality as a shimmering web of discrete events, each precisely ordered by what influences what. Unlike other quantum gravity models that rely on abstract mathematics or hidden dimensions, this theory strips reality down to its most elemental ingredients, a collection of points representing spacetime events connected only by their causal relationships. Picture an endless domino rally, where each domino doesn't just topple, it defines the very structure of time and space by its connection to the next. The theory's elegance lies in its simplicity. Each point in a causal set has no inherent properties, no position, no duration except its place in the sequence of causes and effects. From this minimalist starting point, familiar spacetime emerges like a mosaic forming from countless tiny tiles. If you've ever seen a newspaper photo up close, you've noticed it's just dots, yet from a distance, those dots blend into a coherent image. Causal sets work similarly. The smooth, four-dimensional universe we perceive is a large-scale approximation of an underlying granular reality. This solves a key conflict between relativity and quantum mechanics. Einstein's relativity treats spacetime as a smooth, deformable fabric, while quantum mechanics insists everything becomes grainy at the smallest scales. Causal sets bridge this divide by declaring that spacetime is discrete at its core. It only appears continuous because we're viewing it from too far away. But how could something so abstract make testable predictions? Here's where the theory surprises. If spacetime is fundamentally granular, then there ought to be a smallest possible unit of time and space, a quantum of spacetime so tiny, 100 million of them could fit across a single atomic nucleus. This granularity might subtly alter how particles behave at extreme energies. Some models predict that high-energy cosmic rays, which travel billions of light-years, should show tiny deviations in their arrival times if space-time isn't perfectly smooth. Experiments like the Fermi Gamma Ray Space Telescope are already hunting for these anomalies, and while results aren't yet conclusive, the mere possibility electrifies physicists. Even more tantalizing is the theory's explanation for the arrow of time. In causal sets, time's flow isn't an illusion. It's baked into the structure itself, with each new event irrevocably linked to its predecessors. This could explain why we remember the past but not the future, not as a statistical fluke, but as a fundamental feature of reality's architecture. Critics argue the theory lacks a clear dynamical framework. How exactly do these causal links grow to form spacetime? Supporters counter that its minimalist approach is its strength, avoiding the baggage of extra dimensions or untested particles. After all, if relativity teaches us anything, it's that spacetime is relational. It's not a stage, but the relationships between events. Causal sets take this idea to its logical extreme, suggesting that what we call here and now might just be knots in a vast, ever-growing network of causality. Whether it ultimately unites quantum theory and gravity or not, this framework forces us to rethink the very essence of existence, not as a place, but as a story being written one causal connection at a time. Imagine a world where directions lose their meaning, where moving left then forward doesn't take you to the same place as moving forward then left. This isn't a glitch in reality's navigation system. It's the heart of non-commutative geometry, a revolutionary framework where the very coordinates of spacetime refuse to follow the rules we take for granted. Developed by mathematician Elaine Connes, this theory doesn't just tweak our understanding of the universe, it dismantles the stage altogether, suggesting that at the tiniest scales, space and time aren't smooth backdrops but a shimmering, uncertain dance of relationships where order depends on who's asking. The key lies in a mathematical property called non-commutativity. In everyday algebra, 3 times 4 equals 4 times 3. The order doesn't matter. But in quantum mechanics, certain operations do depend on sequence. Measure a particle's position first, then its momentum, and you'll get a different result than if you reverse the steps. Connes realized this isn't just a quirk of particles, it might be the secret language of spacetime itself. His work replaces the traditional smooth, geometric universe with an abstract algebraic structure where points can't be pinned down because their very identities blur depending on how you approach them. Think of it like a cosmic game of Simon Says. The universe only defines locations relative to the operations you perform, not as absolute markers on some grid. This radical shift solves puzzles that baffle conventional physics. At quantum scales, spacetime isn't just grainy, it's fundamentally fuzzy, with no clean separation between here and there. Non-commutative geometry captures this by treating coordinates as mathematical operators that don't commute, meaning their product changes if you swap their order. The result, a universe where the concept of distance loses its meaning below a certain scale, like trying to measure the width of a shadow with a ruler made of smoke. This isn't just abstract math. It mirrors the behavior of black holes, where spacetime becomes so warped that coordinates tangle into incoherence near the singularity. The implications ripple across physics. By framing spacetime in algebraic terms, Connes's framework unifies seemingly disjointed domains. The forces of nature, gravity, electromagnetism, emerge not as independent actors, but as different facets of a single geometric tapestry woven from non-commutative threads. Even the standard model of particle physics, with its zoo of quarks and leptons, fits elegantly into this structure, as if the universe were solving its own equations through the dance of geometry. Some models suggest this could explain dark matter's ghostly grip on galaxies. If spacetime's fuzzy nature alters how gravity propagates, we might not need invisible particles to account for the extra pull, just a recalibration of how we measure the cosmic fabric. Critics argue the theory is too abstract, divorcing physics from visualizable models. Yet supporters counter that reality has no obligation to be intuitive. Quantum mechanics already shattered that illusion. Experiments might one day test these ideas by probing spacetime's fuzziness. If photons traveling from distant quasars show subtle anomalies in their polarization, it could hint at non-commutative structure tweaking light's journey. Others suggest tabletop experiments with ultra-cold atoms, where quantum coherence might reveal spacetime's hidden algebra. Non-commutative geometry doesn't just challenge our maps of reality, it questions whether maps are even possible at the deepest levels. If Cons is right, then spacetime isn't a thing, but a conversation, a dynamic exchange where the answers you get depend entirely on the questions you ask. In this view, the universe isn't built from places or moments, but from relationships that refuse to sit still, whispering the secrets of the cosmos in a language where order itself is negotiable. What if reality isn't a fixed stage, but a tapestry woven from every possible moment of observation, every glance, every measurement, every conscious experience? This is the spine-tingling premise of the Observers, a theory that fuses quantum mechanics, relativity, and information theory into a vision of existence where observers aren't just passive witnesses, but the very fabric from which reality emerges. Picture the universe not as a collection of objects, but as an infinite network of observer moments, a fleeting snapshots of awareness, each one a knot in the cosmic web where information is exchanged, processed, and ultimately where reality crystallizes. At its core, the Observerse builds on quantum mechanics' most perplexing feature, the observer effect. In the double-slit experiment, particles behave as waves until measured, seeming to choose a definite state only when observed. Traditional interpretations split into camps. Some say consciousness causes collapse, others argue it's just interaction. The observer sidesteps this debate entirely by proposing there's no outside reality at all. Instead, what we call the universe is the ensemble of all possible observer-created moments, each one a self-contained bubble of experience. Relativity compounds this, since different observers can disagree on the order of events depending on their motion. There's no universal now. The Observerse embraces this, treating time as a mosaic where every possible sequence of observations exists simultaneously, and what we perceive as flow is just our path through this labyrinth. Here's where it gets dazzling. Information theory, the study of how data is stored and transmitted, shows that observers don't just record reality, they define it through the act of measurement. Imagine flipping a coin. In a classical world, it's either heads or tails before you look. But in the Observerse, the outcome isn't determined until the information enters some observer's awareness, whether it's you, a camera, or even a single atom interacting with the coin. The real outcome is the sum of all possible observer moments where the coin lands heads and all where it lands tails, with each moment equally valid. This isn't solipsism, it's a democratic multiverse where every observation, no matter how simple, contributes to the tapestry. The implications rewrite our understanding of existence. If reality is observer-centric, then the Big Bang wasn't the beginning of a universe, it was the first observer moment in a self-sustaining chain. Black holes might not destroy information but transform it into new observer states like cosmic data compression. Even death takes on a new hue. Your final moment isn't an end, but one node in an infinite network where every possible version of your experience persists. Critics argue this veers into metaphysics, but supporters point to quantum Bayesianism cubism, which treats probabilities as degrees of belief for observers, not objective realities. Experiments in delayed choice quantum erasure, where decisions made after a particle's journey seem to retroactively affect its path, hint that observation's role is far stranger than we thought. The Observerse doesn't just challenge what reality is, it asks who it's for. If every observer moment is equally real, then the universe isn't a single story but an ever-branching anthology where each consciousness is both author and audience. Whether this theory holds or not, it forces us to confront a humbling truth. We might not live in a universe but as one, a fleeting yet eternal fragment in an infinite mosaic of perspectives. What if the universe needed us just as much as we need it? The participatory anthropic principle, proposed by legendary physicist John Wheeler, turns conventional cosmology on its head with a startling claim. Observers don't just witness reality, we create it, retroactively shaping the cosmos from the Big Bang to the present moment. This isn't poetic metaphor, it's a radical reimagining of causality itself, where the act of observation stitches history into existence, like a cosmic choose-your-own-adventure book being written backward. Wheeler's inspiration came from the eerie behavior of quantum particles. In his famous delayed choice experiment, he demonstrated that a photon's decision to act as a particle or wave isn't just uncertain until observed. It can be influenced by measurements made after the photon's journey has seemingly concluded. Imagine firing a gun at a target, and only after the bullet hits do you choose whether the gun was loaded with blanks or live rounds. The results suggest that the past isn't fixed but fluid, waiting for observers to lock in events by their very act of looking. Wheeler took this further, arguing that if quantum weirdness scales up, then the universe itself might exist in a fog of potential until conscious observers crystallize it. This leads to a dizzying conclusion. The Big Bang wasn't the beginning, but a consequence of observers like us emerging billions of years later. It's as if the universe bootstrapped itself into existence by ensuring its own eventual ability to perceive itself, a cosmic Ouroboros where the end creates the beginning. Think of it like a jigsaw puzzle assembling itself backward. The final piece, conscious observation, snaps into place, and suddenly the entire image, including the edges laid down 14 billion years ago, becomes real. Critics dismiss this as metaphysical hand-waving, but supporters point to the fine-tuning problem. Why does the universe have such precise constants that allow for life? The participatory anthropic principle offers a spine-tingling answer because observers had to arise to make those constants meaningful. Even the cosmic microwave background, the afterglow of the Big Bang, might carry imprints of this retrocausal loop, like whispers from a future that helped shape its own past. Wheeler's vision doesn't just blur the line between observer and participant, it erases it entirely. In this view, we're not bystanders in a preordained cosmos, but co-authors of a story still being written, our very gaze weaving the fabric of reality one observation at a time. The universe becomes less a machine and more a grand collaboration, where existence itself hangs in the balance until someone or something turns to look. Neutral monism offers a third way out of the age-old debate between materialism and idealism. The idea that reality is neither purely mental nor purely physical, but something more fundamental that gives rise to both. Picture a vast ocean where waves represent thoughts and currents, represent atoms. Both are temporary patterns emerging from the same deeper substance. This isn't a new idea. Philosophers like Baruch Spinoza and William James hinted at it centuries ago, suggesting that the rigid separation between mind and matter might be an illusion, a byproduct of how we perceive the world rather than how it truly is. But today, advances in quantum physics and neuroscience are breathing new life into this once esoteric concept, revealing startling connections between the observer and the observed. Consider the quantum measurement problem. At the subatomic level, particles exist in superpositions until measured, at which point they collapse into definite states. The question of what triggers this collapse has stumped physicists for decades. Some interpretations, like von Neumann-Wigner consciousness causes collapse, flirt with idealism, suggesting the mind plays an active role in shaping reality. But neutral monism offers a subtler take. Perhaps the act of observation isn't mental or physical, but a process rooted in a neutral substrate that transcends both categories. Information, neither purely material nor purely experiential, could be the common currency, with matter and mind being two sides of the same informational coin. Neuroscience adds another layer. Studies on consciousness reveal that subjective experience doesn't map neatly onto brain activity. The infamous hard problem, coined by David Chalmers, highlights how neural firings, electrochemical events somehow produce the vivid feeling of tasting chocolate or seeing blue. Neutral monism sidesteps this dilemma by proposing that consciousness and brain processes aren't causally linked, but are parallel expressions of something more primal. Think of it like a hologram. The image and the laser light aren't separate entities, they're different aspects of the same underlying interference pattern. Even modern physics hints at this unity. Quantum entanglement, where particles remain mysteriously connected across vast distances, suggests that reality at its core is deeply relational, a network of interactions rather than a collection of isolated things. Some theorists argue that spacetime itself might emerge from more fundamental, non-spatiotemporal building blocks, a framework where the distinctions between inner experience and outer world dissolve. Carlo Rovelli's relational quantum mechanics, for instance, treats physical properties as context-dependent, existing only in relation to other systems, blurring the line between observer and observed. Critics argue that neutral monism is vague. What exactly is this neutral substance? Supporters counter that physics already deals with equally abstract foundations like quantum fields or spacetime foam. The theory's strength lies in its flexibility. It doesn't reduce mind to matter or matter to mind, but finds a middle path that honors both. If true, it could reshape everything from artificial intelligence, suggesting that true cognition requires more than just silicon, to our understanding of the cosmos, where the universe might not just contain observers, but be, in some deep sense, an act of observation itself. If the universe operates like a vast computer, as digital physics suggests, then it must have fundamental limits, a cosmic speed and storage capacity beyond which no computation can go. These boundaries aren't just technical footnotes, they're clues etched into reality's architecture, revealing how information shapes existence itself. Take Bremerman's limit, a startling ceiling derived from quantum mechanics and relativity. It states that no physical system, whether a star, a supercomputer, or the universe itself, can process more than 1.4 times 10 to the 50th bits per second per kilogram. Picture the entire Earth converted into pure computing power. Even then, its maximum processing speed would be dwarfed by this universal constant, a law as unbreakable as the speed of light. What makes this limit profound is its inevitability. At the quantum level, cramming more information into a smaller space requires more energy, and eventually, you'd need so much that the system collapses into a black hole. Bremerman's limit isn't just about engineering constraints, it's a signature of spacetime's graininess, a reminder that reality has a finite resolution. This echoes the holographic principle's claim that the universe might be a projection of data stored on its boundary, like a cosmic hard drive hitting its maximum write speed. Even if we could harness every atom in the cosmos for computation, we'd still face this immovable barrier, suggesting that information isn't just a tool we use to describe reality, but the very stuff reality is made of. Then there's the Margolis-Levitin theorem, which tackles time itself. It proves that any physical system has a minimum time to transition between distinct states set by the system's energy. A quirk of quantum mechanics means a particle with more energy can switch states faster. But there's a catch. Beyond a certain point, adding energy doesn't buy you speed, it just heats the system. The theorem implies that the universe has a built-in frame rate, a refresh speed for reality's computations. For a single electron, this limit is staggeringly fast, around 10 to the minus 15th seconds. But scale this up to macroscopic objects and you see why our world feels continuous. The frames flicker by too quickly for us to notice the gaps. The implications ripple through cosmology. If the universe is a computational process, these limits define its operational parameters. Bremerman's cap suggests there's only so much information that can ever be processed in a given volume, meaning complex structures like human brains might be riding razor-thin margins of efficiency. Margolis Levitin's time constraints hint that quantum systems could be the universe's optimized processors, running calculations at the literal edge of physical possibility. Together, they paint a picture of a cosmos that isn't just mathematically describable, but mathematically constructed with computation woven into its bones. Critics argue these limits are abstract, untestable in practice, yet experiments with quantum computers already bump against Margolis Levitin's boundaries, showing particles transitioning states at the predicted maximum speeds. Meanwhile, black hole thermodynamics, where information seems to vanish into singularities, may encode Bremerman-like limits at cosmic scales. Whether these theories hold or not, they force us to confront a radical possibility. The universe might not just resemble a computer. It might be one humming along at the exact limits imposed by its own physics, crafting galaxies, thoughts, and time itself from the ceaseless churn of information. From simulation theory to holographic universes, from timeless blocks to quantum consciousness, these 30 theories don't just tweak our understanding of reality, they shatter it completely. Each one peels back another layer of the cosmic onion, revealing possibilities so wild they make our everyday experience feel like a fleeting dream. Yet amid this dizzying diversity, a common thread emerges. Reality is far stranger, far more malleable, and far more mysterious than our senses could ever suggest. Whether we're digital avatars in an alien computer, emergent patterns in a quantum mind, or shadows cast by some higher dimensional truth, one thing becomes clear. The solid, predictable world we take for granted is anything but. What's fascinating isn't just the breadth of these ideas, but how they intertwine. The holographic principle whispers to the simulation hypothesis. Panpsychism dances with quantum Darwinism. Even theories that seem to clash, like superdeterminism's clockwork universe and participatory anthropic's observer-created reality, might be different facets of a truth too vast for any single framework to capture. This isn't contradiction, it's the sound of science and philosophy stretching their limbs, probing the edges of the knowable. And while we may never pin down the ultimate nature of existence, that's almost beside the point. The real magic lies in the questions themselves, in the way they dissolve our assumptions and ignite our curiosity. So where does that leave us, not with answers, but with something even more valuable, wonder? The kind that turns a glance at the night sky into a humbling confrontation with infinity. Whether you're drawn to the elegance of the mathematical universe, the existential thrill of Boltzmann brains, or the cosmic intimacy of the participatory anthropic principle, these theories aren't just about explaining reality, they're about expanding what it means to be part of it. Now it's your turn. Which of these ideas cracks open your sense of the possible? Drop your thoughts in the comments, debate them, defend them, let them collide. And if your brain's still buzzing from today's journey, hit that subscribe button, because this is just the beginning. The universe has more secrets waiting, and together we're just getting started.